Hello and welcome back to Calculus 2. This is section 10.3 on infinite series. There will be a whole bunch of lectures on infinite series, and they will cover 10 different tests for convergence till the end of the chapter. Today we're going to take a look at the overview of infinite series and take a look at 2 tests out of the 10. We start with the definition, which is important. Series is a sum of a sequence. So series is the sum of a sequence. Series is the sum of a sequence. Notation for it would be summation of an. And it's going to go from some value n equals to either 0 or 1 or 2 or whatever. So it goes in from some value, let's put 1, and it can go to a finite number or it can go to infinity. So I'm just not going to put any of these that you are used to from Calculus 1. I'm just going to leave it like this. Because the next thing I'm going to write is that series can be finite, which is summation, and let's say n starts at 1 and goes to 6, let's say, of some sequence, or infinite, in which case summation, let's say, again starts at 1 and goes to infinity this time. It doesn't have to start at 1. It can start at any number, 0 or higher, and it's not any number, sorry, any integer. These are all counting numbers. The meaning of this notation is simply summation n goes from 1 to, let's say, 6 of n squared. What do you have? Well, first around n is 1, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and then you get a number. What do we have? These two are 5, 9 and 16 are 25. This is another 25, and this is 36. So 50, 80, 91, if I did this right. So that's a 4 and 1 is 5, 9 and 4 and 6, 25, another 25, 36, 25, 50, 80, 86, 91. Good. Now, finite ones are not interesting because they always converge. You can always add a finite number of terms. If you go from 0 to 1,000,000, just write a code, and the code will add it for you. Write the computer will add it for you. It doesn't matter. So these were always converge, and that's why they are not interesting at all. The ones that are interesting are the ones on the bottom that can either converge or diverge, which means that their sum, right, for depending on what sequence you get, their sum either adds to a finite number, which is convergence, or to infinity, which is divergence. Now, infinite series can be convergent, which means that you get to add up infinitely many numbers, and they will add to a finite value. Now, you already processed that in your head a little bit when we did improper integrals. You know that some of those improper integrals converged. So it's possible to have infinity and still be convergent. So series is a simply sum of the sequence, and that's literally the end of story, right? Sum of the sequence, end of story. So now we would like to, for infinite series, summation, let's say from 1 to infinity of sum an, we know that there is convergence and or divergence, depending on which one you get. There are 10 tests to learn/use to determine convergence. We are learning the first two today. The first one we are learning now is called geometric series. Alright, so this is going to be now a little bit different than what you guys are used to so far. First off, you are dealing with mathematics that it's no longer continuous. You are dealing with discrete mathematics, which means there is a value, then nothing, then a value, then nothing, and value, nothing, and so on. Some of the things that you would see as common sense are not common sense in this realm. So what I usually do before I teach any of the chapter 10 on series and tests and so on, is I make it clear that the only right way to do this is to memorize these 10 tests to the letter and then apply them where they belong. And if you try to come up with something on your own, most likely will be wrong. So this is what the geometric series test look like, and then we'll see how it's used. If you have a series that looks like this, n starts at 0 to infinity, of a r to the n, series is convergent if r is in between -1 and 1. It's divergent otherwise. This is how simple it is. This is what you must remember. Geometric series is convergent if the value r is in between -1 and +1. Cannot be -1, cannot be -2, cannot be +1 either, right? It has to be in between -1 and +1, excluding -1 and +1, because we don't have equal signs there. Convergent series converge to the sum equals a over 1 minus r. This is the formula to calculate the sum of the geometric series. And now this is it. So the tests will look something like this. And now let's use it in a problem. You have summation 0 to infinity of 3 times 1/4 to the n as a problem. Converge or diverge? Converge. That's it. It literally takes 5 seconds, well, not 5, so 1 second. You look at the problem and you say r is 1/4. That's between the -1 and 1. So converges. And you're done. That's it. No calculating. No integration, no derivatives, nothing. You either know the red stuff or you don't. And you can't make it up. There is no reasoning with it, right? Do we get that? So you have to memorize these 10 tests, the way they are stated. And for most of them, you just look and you're done, all right? Now, since that is so easy, we come up with stuff like this. 0 to infinity, 6 divided by, I don't know, 8 to the n, and then, right, does this converge or diverge? So now this is a matter of how good your algebra is. It converges. You are going to put the 6 on a side, have 1 over 8 to the n. I'm going to write out all the steps, but it's sufficient to look in the first one. And then 6, 1 over 8, everything to the n, and you see it's still in the same form, and it converges because r is 1 over 8. So maybe you have to, massage it a little bit, and then get the form that you're looking for. Summation 0 to infinity of 5 quarters to the n. Diverges. 5 over 4, r equals 5 over 4, is bigger than 1. Diverges. Because the theorem up there states, the test states, that if it's not in between -1 and 1, then it's outside of that range, and it said otherwise diverges, right? This is the otherwise case. It's larger than 1. What does it mean to converge? What does it mean to diverge? Convergent series, like the one on top, means that when you add infinitely many numbers generated by this series, divergent one means when you add infinitely many terms, they will add to either positive or negative infinity. Diverge. So convergence simply means adding infinitely many numbers governed by whatever the series is. Convergence means adding infinitely many numbers ends up being a number. And then divergence means it goes to infinity. That sum goes to infinity. So now you have summation 0 goes to infinity of 3 over 4 to the n. Now you look at this quickly, you say, okay, my r is 1 over 4, less than 1, converges by geometric series test. We'll just put the GS later on, faster. And now, since it converges, I gave you the formula to calculate the value that it converges to. So S equals A divided by 1 minus R. A is 3, 1 minus R, which is 1/4. There we go. Multiply top and bottom by 4 to get rid of the double fraction, and we have 4/3. So this means that when you add infinitely many numbers that are all this, it will add to 4/3. Great. So we have seen 4 problems. They were really straightforward if you know the theorem, the test. And now I want to introduce another problem, which will say summation starts as 2 to infinity, and then we have, let's say, 4, 1 over 3 to the n, and is asking you for the sum. Well, first of all, is this convergent one? It is. Okay, good. Why? Because r equals 1/3 is less than 1. Great. So it's very simple to see it's convergent. You just need to know that test. So we know it's convergent because 1/3 is less than 1. Done deal. Ready for summation? So here's the trick question. What's my a? And you're gonna go say 4, and I'm gonna say no. And you're gonna say, what? It was, in the previous case, it was 3, and it was 3. What do you mean it's not 4? Well, what's different now? Exactly. It starts at 2. The formula in your test starts at 0. So this formula works for that one. It doesn't work when it starts at 2. So even though this is also very simple, we now need to learn the method to shift the counter back to 0 so that we can use this formula to compute the sum. And then we're done with this test, as soon as we figure that one out. So here in blood, we must shift the counter back to 0 in order for the formula S equals A over 1 minus R to work. And now the question is, how do you shift this? How you shift this thing? So you have n equals to 2 to infinity, 4, and then you have 1/3 to the n. What is the thing you don't like, or any one of you? It's that 2. And how can I change that 2 into a 0, which we need? It's an equation, n equals to 2. So how do I switch that 2 into a 0? What should I do? 2 divided by facepalm. Subtract 2 both sides. Subtract 2 both sides. If you subtract 2 on both sides, then the right side becomes a 0. Good. So my new equation over here is n minus 2 equals to 0. Well, I'm not really going to use n minus 2, right? So let's call it a k. But then I have this issue now that it's n over here, and I switched for k's over there. Because the next step over here will say k goes from 0 to infinity, and we're happy campers, right? The problem is when I write the rest of the problem here, I'm not allowed to put n there, because my counter now became k. So I have to change this n. Now, how would you change this n? Solve the equation. Because that then needs to change into some form of k, because k will operate. So we know that k is n minus 2, from where n is k plus 2. So that's a k plus 2 up there. And now we use that algebra formula to peel off the plus 2 part. So summation k equals 0 to infinity, 4, and now peel off 1, peel off another 1, so that's your squared, and then leave the rest as k. If I need to remind you of the formula, that x to the m times x to the n is x to the m plus n. So if you think about this, why I put 2, m plus n. So if you think of this as, let's say, well, it's k plus 1 plus 1, it's k plus 2. So now we say summation, k starts at 0, goes to infinity, and you have 4 over 9, 1 over 3 to the k. So is your a 4? No, a is 4 over 9. So now I can run the summation. It is 4 over 9 divided by 1 minus 1/3. Multiply by 9 to get 4 divided by 9 minus 3. 4 divided by 6, 2/3. When you add infinitely many numbers in that series, they will all add to 2/3. Now, usually on exams, this is where you make a mistake because you don't shift the counter, and then all of the numbers obviously work out to be wrong. But for the geometric tests, right, you simply just look at the value of r. Nothing to calculate, right? You just use your eyes and look. And that's it. It's very simple. But you need to know. You need to know the rule. The second test we are going to cover is telescoping series test. Telescoping series. So these guys have a form of bn minus an, so there is this subtraction in there. So it's not a theorem like the previous one where you look at the r and you're done. This one will have a lengthy procedure that obviously is the best learned looking at the example. So here it is. Summation of 1 over n minus 1 over n plus 1 from, let's say, 2 to infinity. I recognize that this is telescoping series because there is a subtraction between the two parts. And what I'm going to do now is I'm going to break this into kind of two parts. The first part is going to be just start plugging in these values to get maybe first 4 or 5 parentheses. So when you plug in 2, you get 1/2 minus 1/3. That's when you plug in n equals to 2. Then a big fat plus, because it's summation, right? Summation is the plus generator, okay? So for the next term, n equals to 3, you have 1/3 minus 1/4. That's when n was equal to 3. Then for the next term, when n is equal to 4, you have 1/4 plus 1 minus 1/5. And the last term I'm going to write for this part is when n is equal to 5, and that will be 1/5 minus 1 over 6, plus 3 dots. This pattern will continue forever. Now 4 terms, not too good. So here's a very clever method, what they figure out. Instead of having the entire series, if it ends up being You see, what I did is I just did first 4 terms, right? And if I add another 20,000 terms, I'm still not even scratching the surface of infinity. I went from A to infinity, and what did you do with infinity? You replaced it with a finite value B that you can compute with, and then in the limit, you sent B to infinity, right? So it's like infinity is replaced with B, and then B is sent to infinity. So what I'm going to do here for this series is I'm going to do the same, pretty much the same trick. Instead of calculating all the way to infinity, I'm going to calculate to some finite number, let's say finite number k, and then I'm going to send k to infinity. So the other end over here, which I'm going to actually work out backwards, because that's the easiest way to work these things out. What you see me do here is setup is going to be 1 over k minus 1 over k plus 1. That's the last term. It looks the same as the problem. And then the term before will subtract 1 on every k. So I have 1 over k minus 1 minus 1 over k, just k, 1 over k. The term before that, again, subtract 1, so you have 1 over k minus 2 minus 1 over k minus 1. Because this k, when you subtract 1, you get k minus 1. And now we see that a lot of stuff cancels. Negative 1/3 has a positive 1/3 here. Negative 1/4 has a positive 1/4. Negative 1/5 is a positive 1/5. So will negative 1 over 6 get canceled? Yes, because the next term will start with 1 over 6, right? So this will be canceling, and I usually just cross out this way, so I know that it cancels with the next term or 2 terms down the line. Same happens here. Positive 1 over k, negative 1 over k. Positive 1 over k minus 1, negative k minus 1. So if you are already having one of these where both cancel, that means that after that everything cancels. So this one will definitely cancel with something that we don't see in here. So what's left? The only thing that's left is 1/2 up there and negative 1 over 1 plus k plus 1 on the bottom. So this is equal to 1/2 plus the limit. K goes to infinity. So this is me fixing my mistake from before, right? Not mistake, I mean, what I'm doing now is I'm sending k to infinity, because remember I replaced my infinity with k, so it's a finite value, so I can compute, and then now I know that k needs to go to infinity, so I'm just going to send there. But this is 1 over infinity, which is 0, so 1/2 plus 0 is 1/2. The C in a circle converges to 1/2. So converges to 1/2. Let's take a look at one more time at this whole procedure. You will get a sense of how many of these terms you need to write. I'll tell you after another example. But right now, let's say 4 or 5 terms on the front end and 4 or 5 terms on the back end. They will always be symmetric. There are some problems where 3 would be enough, front and bottom. just like this problem, 3 was enough. But then there are some problems where you will have to have 5 or 6 in the front. And I remember my Calc2 exam had a 5. I couldn't figure out because I was memorizing this without any context at all. And on the exam, there was a problem that I had to go all the way up to 5 terms to see the pattern, but I only did 3 terms. I didn't see the pattern, and I just made a guess, and obviously got the problem wrong. The way to do this is to keep writing terms until you have one full parenthesis cancel. As soon as the one full parenthesis, the first one that cancels fully, you're out. You don't have to write more terms. So as soon as I see negative 1/3 and positive 1/3, and then in the next part is this, that's all I need to write because I already have one parenthesis which cancels both terms. And then that guarantees that every next one will cancel all terms. And the same from the back end. Let's take a look at another one from the textbook, as from homework, I mean. All right, so they don't have good problems of what I wanted to illustrate here. So let's start at 1 to infinity, and over here I'm going to modify the problem. 1 over, you can use k, you can use n, whatever. 1 over k plus 1 minus 1 over k plus 4. So now we write out, right, when you have a 1, the first term is 1/2 minus 1/5 plus, so this is where k is equal to 1. The next one is when k is equal to 2, we're getting 1/3 minus 2, 6, 1 over 6. So that's k equals to 2. K equals to 3 is going to be 1/4. See, we still don't have calculations. If you take a look at these two parentheses, they have all different numbers, right? If at least you had a pair, right? But you don't. So we have 1/4 minus, and now when k is 3, that's going to be 1 over 7. Still no match, right? Plus k equals to 4. When k is equal to 4, you get 1 over 5 minus 1 over 8. Finally. Plus, I have to keep going, 1 over 6. That was, right here. So it's 5, yep, 1 over 6. So for k equals 5. And minus 1 over 9, right? So look what cancels. Negative 1/5, positive 1/5. Negative 1 over 6, positive 1 over 6. My question is, do I have a parenthesis out of these 5 terms that canceled both terms? No. So I have to do more. Plus, and now it's 1 over 7 minus 1 over 12. And we can cancel what we are missing. I mean, we can cancel this 1 over 7. It's still not there. That means more terms. Remember what I'm looking for. I'm looking for the first parenthesis that will cancel both numbers. So I have to write another term. What happened? I don't have another 12.
1 over 10.
Oh, 1 over 10? Yes. Yes. Thank you. 1 over 10. So now we have 1 over 8 minus 1 over 11. Plus, and here it is, finally. This 1 over 8 will cancel negative 1 over 8, and we just got ourselves the first parenthesis which canceled both terms. That means we can stop and work on the tail end of the problem. Now for this, I'm going to set up a few of these. The last term is always the same as your problem, except now we have to use n's because we will send n to infinity later. So it's 1 over n plus 1 minus 1 over n plus 4. Now the previous parenthesis, right, the parenthesis before this one, is going to reduce these denominators down by 1. So it's 1 over n minus 1 over n plus 3. And then take away another one. So minus n minus 1 minus 1 over n plus 2 in this case. And the next one over here is 1 over n minus 2 minus 1 over n plus 1. Oh, okay, so at least these guys cancel now. How many terms to have a symmetry? 1, 2, 3, 4, 5, 6, 7. We will have to write 7 terms. I wrote only 4. So what is the summation equal to? It is equal to all of the numbers that you didn't get to cancel, which is 1/3 plus 1/4. So we have 1/3 plus 1/4, and then plus the limit, n goes to infinity, of all of these. But guys, as n goes to infinity and n is in denominator, then it will just make all results to be 0, so we don't have to care about it. See, if I have the limit and I just add any of these terms, 1 over n plus 1 minus 1 over n plus 4, right? If this limit is brought to me, I just say, well, it's 0, because 1 over infinity is 0, and you just have a 0 for that one. So the whole thing over here is 0, right? That's what I mean. So now we have that the sum is equal to 7/12, right? That's the sum. The tail end did not contribute to these calculations very much. And now I want to go back and talk about the amount of parentheses. How far apart are these guys? They are 3 numbers apart. 3 ticks, if you want to talk computers, right? So there are 3 numbers apart from 1 to 4. You see that you had to go through 1, 2, 3 parentheses before you ran into a parenthesis which had 2 cancellations, and you can stop. Now, previous example, the difference between them was 1. So there was only 1 parenthesis before you got the one that cancels both. So a lot of patterns here. And probably this is the probably most trickiest of the tests, because in some cases you don't even recognize the problem. And obviously that creates issues. Look at this. Summation, start at 1, go to infinity, of 1 over n squared plus 13n plus 42. How do we transform this one thing into a subtraction of 2 sequences within a series, so that we can run the procedure and compute? How do we transform this division into subtraction? Think about it. And talk to others too. What? Excellent. Yes, factor denominator.
Plus 6 and plus 7.
I'm sorry?
Oh, we're doing it.
Yeah.
Oh, sorry.
No, it's fine. I'm happy that you did it. So you said, so I don't have to do it. So you said factor it, and we said yes, of course, factor it. 1 over n squared. No, what did you say? N plus 6, n plus 7. Well, this still is not a subtraction of 2. Yes! Use the partial fraction decomposition to turn this monstrosity into 2 fractions that are subtracting each other. And then you can do the telescoping. So now we have to do partial fraction decomposition. Green. Use partial fraction decomposition, because it will turn that multiplication should turn into sum of 2, but whatever we put for b will be negative eventually. All right, so I have a over n plus 6 plus b over n plus 7 to be 1 over n squared plus 13n plus 42. Cross multiply on the left, we have an plus 7a plus bn plus 6b equals to 1, because denominators at that point cancel. Now obviously this is on your exam on Monday, so you already know what to do here. We have a plus b equals to 0, because there are no n terms on this side. And then 7a plus 6b equals to 1. So same partial fraction decomposition that we used for integrals are now used here to separate the telescoping. So now you multiply the top equation by, let's say, -6 to eliminate b, and you get that a is 1. when you, well, let me write, when you multiply by negative 6, you get negative 6a minus 6b equals to 0, and you have 7a plus 6b equals to 1. When you add these two equations, you get that a is 1. And when you look at the a plus b equals 0, then I immediately know that b is negative 1. And that's exactly what I needed. B being negative 1 means that that second one is subtraction. So now I have summation. This is our previous problem. And now I'm going to have two series in here. A, which is 1 over n plus 6 minus 1 over n plus 7. So we used partial fraction decomposition to come up with these two formulas that are subtracted. So now I get to do the patterns. So for n equals to 1, I have 1 over 7 minus 1 over 8. They are 1 apart, which means that this parenthesis that I write here will be the one that cancels. Plus, when n is equal to 2, we have 1 over 8, comma, negative 1 over 9, plus, the next one is 3, so that's 1 over 9, and so when it's 3, it's negative 1 over 10. Now I see that this 8 drops right here, and the 1 over 9 drops this one. I do have the parenthesis which canceled completely, which means that for the rest of this calculation here, I don't have to worry about, because this one will cancel with something in here. I mean, with positive 1 over 10. Actually, that's on our next term, right? Because you can see that the first number, it goes 7, 8, 9, and then the next one will be 1 over 10. Plus, and now we have the tail end. Now for tail end, I'm just going to set up 3 of these. And you always start working on the last one. Work your way up. So, what do I have? Hold on. Series? All right. So 1 over k plus 6 minus 1 over k plus 7. You cannot use the same variable here and here. So now, one term before this one is 1 over k plus 5 minus 1 over k plus 6. One term before that is 1 over k plus 4 minus 1 over k plus 5. Because it's the one term before, so each k gets subtracted by 1. Since we have those integers, they just combine with them. All right, so look. Again, 1 from the end cancels both. See? You have 1, because they are 1 apart. You have 1, and then the next one is the one that cancels. When you look at from the back, it mirrors the same behavior. You have 1, and then here's the first one that cancels all of them. This one will cancel in here somewhere. I mean, in the previous term. So what is the answer? The answer for this sum is, well, 1 over 7 survived, plus the limit of negative 1 divided by k plus 7 as k goes to infinity, which is 0. So the whole thing is 1 over 7 plus 0 and 1 over 7. So the entire series converges to 1 over 7. We had to use partial fraction decomposition in this problem. Come on, how awesome is that? Gotta see more enthusiasm, right? Now, not every telescoping series is going to be convergent, obviously, because remember what you're doing at the end. You're taking the limit as n or k goes to infinity. That can go horribly wrong, right? Because those limits could end up infinities. And what's 1 over 7 going to do if there is a plus infinity next to it, right? It's going to talk to it? No. Want to take it outside to talk to it? No. Definitely not that one. So, because it's infinity, hey, right? So they could be divergent. One of the favorite ones, I think it's like ln n minus ln plus 1 or ln n plus 1 minus ln n. Either way. One of those two is the divergent one. And you can just write out these parentheses like this and start canceling. So if they are 1 unit apart, you will have that 1 unit. And then the first parenthesis after that is the one that cancels both values and from the tail end as well. Now, at the end of this lecture, I'm going to write in blood, geometric series and telescoping series are the only 2 series out of 10 that you know what it converges to. So the next 8 tests, if you have convergence, you have no clue where they're going to, what number they add to. So that's why these 2 are first. You don't apply them first. There will be something else called divergent one that you will try first, just like you always try U sub first. But we need to write here geometric and telescoping series are the only 2 tests which can tell which value the series converges to. Geometric and telescoping series are the only 2 tests which can tell us which value the series converges to. That's it. You will have integral test, root test, ratio test, divergence test, all of these tests. Alternating series comparison, limit comparison, direct comparison. These are all the tests, all 10. Out of all 10, only this one, and P series. I forgot P series. Poor things. We'll talk about P series after the exam on Monday. That's it. That's it. Geometric series, need to know the formula, obviously. Get that R quickly. And if you need to shift the parameter, shift the counter so it matches, then you just shift the counter. Guys, shifting the counter is extremely important because if you're taking differential equations. Anyone taking differential equations? Okay, I'll show you eventually why. So you must know shifting the counter, otherwise you're doomed. Let's see. Bye.